Okay, so we were doing filtering. Okay, said that the filtering is conditions. Okay, but that will be only applicable when the filter is a linear. You see what we mean by non-linear filter. So if you have a non-linear filter, then there is no condition. Although the process is same, okay, but condition is not there. Okay, so what we did, we start this lecture, this set of slides with the condition. So we said filtering is the condition. Then we said, okay, a simple form of the filter is the mean or the average filter. It takes the average of the neighbor pixels assigned to the middle. And what it does is like it smooths the image. Okay, why smoothing is important? Because to reduce noise, because we know that there is some randomness. If the noise is there, there's some randomness. Okay, so when you smooth it, it reduces the noise. Other application of the smoothness is that when we don't need a small variation, so we just try to remove the small variations, try to focus on the big variations. Okay, let's say object detection for second. Then also what are other applications of this can be used in a filtering as the filter in our mobiles. For example, if you want to remove the resources from SCM or something like that, we can help us filter that. So this average filter or the mean filter was the simple filter in which we assign all ones or same way to all the pixels. Okay, but that in reality, if you see the pixel that are near to the pixel of concern, it has more correlation than the other one. So why not to weight this pixel more than the away to that pixel? Okay. So one of if we do that, Gaussian is the function that defines this. Okay, because as we move away from the mean, okay, which is the middle or the middle one, it becomes like diagonal. Which makes sense. Yes. And we said that what is a 2D? Okay, so the Gaussian filter, one variable is what? 1 by under root 2 pi sigma square e power minus f square by 2 sigma square. Okay, so this is 1D or Gaussian, which is actually how it is like this, but it should be because here I assume that S is a zero mean, so it must be the mean should be 0 here. And what is the variance? This is the variance. Okay. Yes or no? That's correct. Fine. Okay, so from this, how I can do a 2D? As we said that one of the property of the filter, not all filters, but one of the property that we want is the separable. Okay, so what is the separable filter? For example, we have filter d of st, that should be d of s d of t, right? Yes. So if I just now in the case of Gaussian, this is 1D Gaussian t s, and if I put t here, I get another filter on another direction. Okay, so what it will look like? It will reduce to this one. Yes or no? Yeah. So he was asking about the covariance. Okay, so covariance is not there because the s and t. Where is s and t? Is this dependent or independent? Dependent. S and t. No, s and t. X and y are dependent or independent? X and y. X and y are independent. So if you have a Gaussian variable with two independent, multivariate, let's say, from those independent, you will get this thing. Okay. So is this clear or not? I think we already discussed it. So if I do this, I will get this. Assuming that assuming that you have the variance of t and s are same, which is same, because we need a symmetric filter. Huh? Okay. Yeah, both this is like this. Okay. Yes. This is one probability with two independent variable, you will get this. But the separable, we already talked. What is separable? When you have this property. Okay. So assuming that the Gaussian filter is separable, this is one Gaussian filter, there's another Gaussian filter. If I put the same here and here, I get this equation.
But what is the equation again behind this?
This one?
Yes.
This is separable.
What is the equation to make it like this?
2D. Yeah, 2D should be a 1D, two 1D filters.
Yeah, I know, but why you make it separable? Because it has a property. What we said,
the filter should have a property of separability.
Rank 1.
Yes. Yeah. Okay, so if you just note it down and read the last section. Okay. Okay, so when in order to find that filter, it's very easy. These are for the filter, the center is the origin. Yes or no? And then you go minus 1 0, 1 0, and x and y axis. So just put these values into the equation and you get this filter. And the 3D view of the same filter is this. We have a 1 inside in the middle. Then this one will be. I get okay. So this is 0.3. This is 0.3, right? And then then 0.6. So yeah, I cannot. Okay, this is 6. Okay, this is 0.3. Okay, the visualization of this is very important when we are dealing the frequency domain. So please try to visualize everything in 3D, so it will give you more insight. Okay, so this is again we said that this is the filter, the same filter, but we tried to have some nice pattern of it to make it integers. What we did, we just multiply with 4, divide by 4, and round it off to get some nice pattern. Yeah, these are just showing the amplitude. This ring is 0.6. Okay, if you see here, we have 1, 0.6, and 0.36. 3. So these are just showing the rings that these are the amplitude, just to make the picture more visualizable.
Yeah, definitely. This is 0.3. This is 0.3679. This is 0.60 and then 1. Okay. Okay, so now the thing is, what should be, one is I give you the size, or you can try and do the size of the filter, let's say 3 by 3, 5 by 5, 7 by 7. But how big? Okay, this again depends on the, because it's die down, and we know that, so the general rule is after 6 sigma on both sides, x and y, or s and t in this case, is significant. Or after that, it's not significant. Okay, so in order to find the length of the filter, 6 sigma is the standard deviation, right? Sigma square is the variance. And then seal it off to get the length of the filter. Yes or no?
Again, this, why did you choose 6 sigma?
After this, the value of the machine curve is not significant.
To 0, but why you put it into our consideration now?
Because this can be a maximum length of the filter.
Maximum
Length of the filter. Let's say sigma is 2. So filter length will be 12 by 12. Okay.
After this, will be your
It will be
0.
yeah, it will be 0. In other words, if I reach left, the effect will not be there. Okay, we have an example here. So I think this is the same thing, but now see, what is the effect of sigma? What is the effect of variance? Less variance versus more variance. What will happen? What will happen if we have less variance or more variance? Yeah, so wider when we have more variance, right? More variance means more variance, right? Less variance, less spread. Okay, and more spread means that we are actually taking account of the more pixels around our pixel of interest. Less means less, right? So it depends on how it will look like. So sigma 2 versus sigma 5, it depends. Okay, just for example. Okay, so now you see here sigma is 7. Okay, so if sigma is 7, how much should be the length of the filter? It's sigma 43 by 43. Okay, and then 85 by 85. And if I subtract them, I get 0, which makes sense that increasing sigma is 0 difference after 43. This is just an example.
7 times 6 is 42. Why not?
Because we need odd number, right? Because it might not mandatory, but it's easy to visualize it because we have to assign filter value to some place. If we have odd, it's easy to assign in the middle. If even, which one consider? This is like 21 by 21 and 43 by 43, so still you can see the difference is there. So it means 0 difference after 43. Here can be seen that more variance, more blur will be there, right? So this is just another example. The Gaussian in 3D will be look like something like this in a discrete format, as you will get this. Now the important thing is the smoothing effect by both filters. We have Gaussian and we have average filter, right? So what is the effect of both of them? If you see the same size of the filter, you can see that this is more smoother as compared to this. So you are saying vacuum blur. This is more blurry. This is a bit smoother.
The picture is more clear than doing the average.
Yeah, so you can say more smoother, but not that much blur. It's smoother and blurred together if you want. So now see, we saw this image before. So this image, if we subtract this image by this, we get this. Fine. So we can also do the same process, like clear this image from the shadow by using our filter. So how to do this? What are the frequencies we are? So if we focus on this, what are the frequency we are looking at? Can you see any frequency here? Can you see any pattern? Some variation? What is frequency? Variation, right? Variation? Yeah, what variation, right? So variation, which type of, let's say if I have the shadow and I have this chessboard, right? So this shadow has, if I compare the frequency of shadows versus the frequency of chessboard, which one is higher, which one is lower? Chessboard has more variations, right?
Yes.
So if I plot it, it is more frequency, right? Black and white, so like this. Okay, if I just take one line, it will be high, low, high, low, high, low. But if I just have the shadow has very small variation from dark to white, it's like very small. Fine. Okay, now our previous concept of using the filters. When we are using the filters like the average and the Gaussian filter, what it was doing? Which frequency we are suppressing and which frequency we are allowing. So we are actually smoothing it. It means that we are, it's a low pass filter, right? So here as well, in order to get either the chessboard or this, if I apply that filter, what I will get? We get the shadow, right? So if I apply a low pass filter onto that, okay, and that filter size is 2048 by 2048 size. Okay, if I apply this one with the Gaussian kernel, yeah, so I will get this thing because I filtered out the high frequencies.
Is the size of the Gaussian?
No, sorry, the size of the filter is 512. The size of this image is 204 and the size of the Gaussian is 512. With k equal to 1, it's minus 1. Okay. So what if I do this? It means that I am basically smoothing the image. I smooth the image means that I'm low passing. I have the low pass filter or maybe low pass the frequencies. Okay. So this is the only low pass frequency. So now I have the shadow and this. I can subtract this to get this. Now here again, one of the applications. This is one application was the smoothing. The other application was removing some impurities. Okay, or distortions. The third can be, let's say, I don't want these small stars, but the big ones. So what I do is I do smoothing and then do some thresholding. Okay, just threshold up, after or below. The other application is I want some big galaxies, not the small stars. Okay, this is another application. So I smooth it out and just try to find the big ones. Okay, this is again Gaussian filter example. We just read the image, then find the Gaussian blur kernel of 5 by 5, and then I just convolve, okay, to find out this is a Python code. And okay, and I think I don't have the MATLAB code, but yeah, you can do the MATLAB as well. Okay, what are the scenarios where we cannot use the average filter? Okay, so one of this is called the average filters are good for random noise, but when you have a salt and pepper noise, what is salt and pepper noise? Like some of these points either go 0 or 1, which belongs to salt and pepper, right? Black and white. Okay, so this is what it is. And if I apply, okay, like this or this, okay. So let's take an example and see if I apply these filters onto the image that has salt and pepper, what will happen? So if you see this, it becomes blurred, but it does not remove the salt and pepper. So then what should we do? We use another type of filter which we call the nonlinear filter, or also called the order statistics filter. Okay, so one of the filter we call it the median filter. Now see, in the salt and pepper, some pixel goes high, some low. Okay, so if I take the median value, I think this will make sense, right? Okay, so that's why the median filter is good for the salt and pepper type of noise. What is median? Now, the middle value. So let's say I have these points. So what will be the median value here? 1, 2, 3, 4, 5, 6, 7, 8, 9. So fifth one will be the median. So now how to find it out? The procedure is similar. We have to find a box around the image. Let's say this box here. Let me see. I will just plot it here. Like we are doing for the convolution. So what in the convolution, what place the filter here? Okay. And term with that multiply and then assign in the middle. That's right. Okay. This is what we do. So here I have to place the filter here, but instead of multiplication and addition, I will take all the values. For example, these values are this one: 10, 20, 30, 20, 20, and 15, and this. So first I have to sort these values. Okay, sort from low to high. Okay, which I did here. Okay, and then take the central value. Okay, or the median value. Okay, so the median is 20. So once I get that, I will assign 20 to this image, and then slide.
So we remove the US and
Yes.
black and white.
Yeah. Okay, clear. So if I have image with the salt and pepper noise, if I apply Gaussian filter, I get this thing, not improved. But if I use the median filter, see the improvement here, better. Okay. So then why not min and max? If you have median, why not min and max? Okay. So min and max means that, okay, I take the same filter, and in that filter, what is the minimum value? I assign the minimum. Okay, so this is minimum, and then so same for the maximum. Now, what is the advantage of minimum and maximum filter?
Sometimes only sort, sometimes only.
Yes. Yeah. This answer, yes, is one of the answer. Okay. Sometimes also used for edges enhancement or reduction as well. But yes, this is one of the things. That let's say you have only sort, so median may not work. Okay, because because if you have just sort, means that you have the high values. Okay, so if I cannot take the max one, but I have to take the minimum one. So this makes sense. Okay, so I'm removing the max one from that part. Okay, is this clear? Okay. Again, I think this is just an example that what will be the median value in there. Okay, so first you have to sort, and then you have to find the mid one. Okay. Yes. Any question up till now? And this is again an example. If you take this, sort it, and then find the middle one. Make sure that this min and max are non-linear filter. Why? It's a non-linear filter as compared to previous average filter, Gaussian filter, which was linear filter. Why this is not linear?
The numbers here, we just put them in order and take the one in the middle. So
yes,
it's very random. I changed like
what is linear and what is non-linear?
H1 plus A2.
Yes, so that property is not satisfied by median and max and the properties. And if somebody says why it's non-linear, you have to show them with the property that a linear system has. Like I proved one of the examples of multiplication. Okay, then we just try to use different type of padding just to give you more insight. Okay, this is nothing. I think it's very easy. Just zero padding, do the same thing, or maybe the mirror or something. Okay, and this again some example with salt and pepper. Median filter is performing better. Even if you increase the size of the filter in Gaussian, it does not improve. Okay, one of the things that let's say if I take this image with the salt and pepper and compare median, min, and max filter. Okay, so you can see that median, this is min, and this is max. Okay, so which one is better and why? Median is better, and why not? What's the problem with min, and what's the problem with max? This one, but in general, what happened? The min becomes more darker, max becomes more brighter. So that's why for salt and pepper both together, this is good. But if only salt is there or pepper is there, then I can use min and max. Okay. Okay. Now we discuss the smoothing, right? So what is the inverse of smoothing? Sharpening. Okay. So in the smoothing, what we did? How to smooth the image? Average. So what is the inverse of averaging? What is average? Just addition. And the opposite of addition is subtraction. Okay. So in general, I will just give you some details. But if you subtract pixels, you will get the sharp image. Okay. How? We have some definitely solid background about. So let's discuss this. Sharpening basically highlights the transitions in the intensity. Okay. So if you have transition, I highlight that more to make it more sharp. Let's say there is an edge space. So the background of the face, there is some transition, and that transition is highlighted means that I'm making the image sharper, right? Yes or no? Okay. So again, as I mentioned, smoothing is analogous to integration, right? Then the sharpening is equivalent to differentiation. Okay, and what is integration in discrete? It's addition, right? Which we did in the averaging. So what is the differentiation in discrete? It's a difference, right? But anyhow, we'll discuss this again. Okay, so image differentiation enhances the edges and the discontinuous, like noise and de-emphasized areas of slowly varying intensity. Okay, so where there is slow varying, like smooth, it will not change, but where there's some transition, it will change. Okay, now let's discuss what do you mean by the first order derivative. What are the properties of the first order derivative? First order derivative, it is zero when we have a constant intensity of constant values. Okay, if you have a constant value, a function has a constant value. If I differentiate, I get zero. Yes? Okay. It is non-zero at the onset of the intensity step or ramp. So let's say you're going like this, and suddenly you have a step. So at that point, there's a jump. So I can say that this is x minus 1, let's say. Sorry, x plus 1. Jump, right? So if I differentiate it, it will be a non-zero value, right?
Yes.
Okay. Because of the sharp transition. Similarly, ramp, onset of the ramp, not the ramp itself. Then you are going like this, and then you have ramp is linear. Okay, so you get ramp at that point where you start it. It means that there is some transition happen, and that derivative will be non-zero. Okay, and it is non-zero along the intensity ramp. Let's say I have ramp is non-zero. So yeah, constant. It will be constant. If I find derivation of the linear, it will be constant value. Okay. Okay. Now, yeah. Now the second order derivative. If I take the second order derivative again, because if I take a derivative of this, again it will be zero. A constant. First derivative will be zero. Second will be zero. Of course. Okay. This is non-zero, but if these two are constant, the second derivative will be zero. Okay, so this will be a constant like that at the onset of the intensity. What it will be? Yes. Okay. Yes, the initial jump. Let's say you have x squared or something, and then you just have a function. So it will be a non-zero quantity. We'll see this. Okay. So only this is non-zero. Then again, let's say you have a ramp. This is easy. These two are easy, right? If you have a ramp, I take a derivative, you get a constant number. Again, I get a derivative, I get zero. So it means that second derivative only become non-zero if you have some transition. Okay. Otherwise, it's zero. If it is constant, either just constant straight line or a linear even. So it means that if the intensities are constant, the second derivative will not give you any information. It will stay the same. But if there is some transition, the second derivative will give you some value. Okay. The conclusion is if you have a constant values of anything, the derivative will be zero. Okay, first derivative, and the second will be zero. But for a constant ramp like this one, the first derivative will be non-zero. Although for this type of curve, I'm not interested because there is no edge. Okay, so if I take the first derivative, then the second derivative, first derivative will make it constant, the second derivative will make it zero. So it means that the second derivative only will be non-zero when we have some transitions, like something like this. So here it will be non-zero second derivative. First has the disadvantage that fine, this is zero, okay, but this is non-zero, it's also okay, but this is non-zero, which I don't want because this constant intensity I don't want because I want to plot the edges. Okay, let me show you an example and you will understand more. Okay,
So we can only detect this edges by only the second derivative.
it can be first, but first will have some limitation as I mentioned for the ramp type of thing. Okay, but there are filters that rely on first as well, but second is better. Let me show you a simple example. Okay, so let's say this is an image. Okay, this is an image, and I take this line. Okay, so this is this line. Okay, the intensity was 5, then moves to 4, 3, 2, 1, and like this. Okay, so if I take a first derivative of this, okay, how I take it, I will just discuss it, but just to give you more insight. If I take a first derivative, you can see here, okay, that this is only, otherwise it's a constant, only at point where there's a transition, you get some transitions, otherwise it's a constant. Okay, if you take the second derivative, it's more smoother as compared to first derivative. And if I just compare, see these black ones are the first derivative and the other ones are the second derivative. So if I take this curve, plot both of them, the second derivative is much smoother unless there is some transition. Okay, transition, then it becomes this. However, if you check that is actually although constant, but there's some edges not there. So what is derivative now? Okay, mathematically I can define the difference between x and another small delta x in continuous domain. Okay, with the delta x goes to 0. Now, this definition, if I apply to the discrete, become very simple. Yes or no? What is delta x? One x and the other x, the difference is one is one sample. So it means that delta x in our case is 1. So this becomes very simple. So what do you mean by this? Fx is my sample and fx minus 1 is the previous one. So if I just subtract them, I get the derivative, the first derivative. Okay. So now the problem is that should I consider previous one or the next one or maybe both? So based on this, I have either the backward differentiation, can be a forward differentiation, or can be a central differentiation. Okay, based on all these three, we have 3 types of filters.
The last one is interesting. I'm jumping to steps.
No, I am on of x.
Last one, simple.
Still I'm on. This is what I'm saying. My point of interest is f of x. Okay. So here what I'm doing, my f of x minus the previous one. This one, f of x minus this one. And these two, I take forward and backward, assign to the new pixel. Okay, let me, it will be clear. Okay. Okay, fine. So can now again, still this is a 1D case, huh? 1D case, and then I will get my 1D case and go to a 2D. Now see what I'm doing here. I'm taking a signal, any signal.
And take that.
In order to sharp it, what I'm doing is I have, let's say, any signal. Okay. So in order to sharp it, I take that signal or say a sample, either the forward one or the previous one. I subtract it and assign to same location here. Okay. Similarly, the other either here or here, whatever I'm using, and assign to this point. This is what I'm doing. Okay. So basically, I do the same thing using convolution. Yeah, perfect. Okay, let's focus on this one. So I'm taking x f of, this is my x f of x. The previous one here is 0, so I will get this thing. Then I subtract these two, get this. Let's take this, these two. So I may get, I don't know. Okay, and similarly and so on, right?
Yeah.
So I'm taking one and subtracting the previous one. Can I do this thing using a filter?
Yes, only the one. This is the
So if I just assign a filter with value what?
one. The one.
One and one negative one. Yes. Okay, and convolve with this, I get yes or no. Okay. Similarly, what about this one? Negative one, positive one. What about this one?
Positive one.
Convolution of plus 1, 1, and convolution of
One.
1, 0, 1.
1, 0,
1, 0, minus.
minus. Okay. So yes or no? It's easy, right? So because in order to have symmetry, I just put the 0 for all because we have it 3 by 3 because we should have odd numbers. Okay. So this is for this one. Okay. I just convolve with the signal, I get the result. I convolve with this and convolve with this to get the difference. If I do this with one signal, what I will get? I get the edges highlighted. Okay. Okay. Good. And this is again the example. Let's say I have a forward differential derivative minus 1, 1, and 0. If I convolve this with this, so what I'm doing? I'm taking this number, okay, subtracting with this one, right? And so on and so forth. Okay. So this is what I'm doing. Huh? Okay. Now in 2D. Not 2D, still the same. Just wanted to see that what is the effect of if I take, now I know that what is the derivative, right? In this way. So let's see what information it is giving in the real life. Let's say I take an image and I take this line, which is a 1D signal. Okay, this line is basically this line. Okay, all these are the intensities. If I take the first derivative, what will happen? If I take the second derivative, what will happen? So if I take the, let's apply this differentiation, which is the forward differentiation. Okay, so let's see what will happen. Okay, so if I apply this, I have these numbers, I subtract 4 minus 5, 3 minus 4 like this and plot it. So you can see that this have more transition when there is this has more some values, big values, when we have a transition here. Yes or no? Yes. Okay, the only problem is if you have a ramp, still it is a non-zero. Although it should be 0 because I'm expecting that my derivative is basically highlighting the edges. But here, if it is non-zero, it means that there is some issue with the first derivative, which I already talked. If you have a ramp, it will be non-zero. So this is a problem. So that's why we move it to the second derivative. Now, second derivative is derived from the first derivative. What is second derivative? I take previous and this and minus 2 of this. Okay, this I call it the second derivative. Okay, instead of the first one, I was just taking one sample. Okay, now I'm taking 2 samples and assign minus 2 f of x. Okay, and again, there is some mathematics behind it, but we don't need to do it. You just stick to it. Okay, so again, if you see this, the ramp is still because it's a constant value, right? So only when there's some change, like here, you get sharp. Here there's some transition, you get sharp. Here you have again this one, then this one, and then this one, and like this, and you see it becomes constant. So this also becomes constant. So this is highlighting the edges. Yes or no? So if I plot both the first derivative and second derivative, you can see that the first derivative is still non-zero when there are ramp, right? This is clear. That's why we go to the second derivative, okay, which is much better. This is just what we did, the same thing. Okay, up till now, the second derivative that we saw was 1D.
Yeah.
Okay, but in images, we should have 2D. Okay, so how to define a second derivative in 2D? So the Laplacian, we know about it. That's the Laplacian transformation. He has simple formula that the second derivative in 2D is sum of the derivatives in x and y axis. Okay, so if we do this, what it means, I have an image, on x-axis I apply the second derivative, y-axis I apply the second derivative, and then add the 2 images, I will get the edges of the
derivative.
Yeah, of course. So the path is a function of xy. So if the derivative is a function, yes. But anyhow, yes.
So like you just add the whole things in 1D.
Yes, you do 1D on x-axis, then on y-axis, and then add this.
Which will become 1D.
No, why?
Because if we have, give us an example before of this.
Okay, so what is this? This is 1D, right?
Yes,
But
x and y.
X and y. But since this is a partial derivative, because f is a function of xy, so I keep the y constant and just do the x.
Okay.
Which previously there was no y, right? Because it was just 1D. Okay, here I took the constant, okay, y constant, and now for the y-axis the same thing. Yes or no? Same thing, but x constant. Yes? Okay. Now put this here, what you get?
This one.
This thing, right? So what it means that in order to basically sharp the image, I add all the neighbors, 4 neighbors, okay, up, down, left, and then subtract by its value.
which is this guy.
which is in terms of the filter, that will be this filter. Yes or no? Okay, so if I convolve my image with this, I will get the sharp. Okay, as I already mentioned, in image processing, sometimes there's theory behind something, but sometimes the people grab the concept and try to modify it. Okay, what is meant by this? We already have this thing, right?
Yes.
But somebody comes up that why not we just do the other way around? Okay, plus to minus and minus to plus. Maybe they get some enhancement in some of the images they were using. Okay, so these are just a variant of the same thing. Then they say why we are having 0? Why not just keep it 1? When you take the difference of the whole edges, whole neighbors, instead of just these two. And if I take the whole edges, one thing that we should have in our mind is the sum of this should be equal to 1. Okay, so if I assign 1, 1, 1, 1 here, I have to make it minus 8. Okay, and similarly, if I have this, why not I have this? So this is
So some of these will be 0.
you're right, for this sharpening it should be 0. So let's quickly just have some example. If I have, let's say, this mode image and I apply Laplacian filter to it, what I will get the edges. Yes or no?
Yes.
Okay, so this is the same as this, just I increase the brightness. Now, this does not sharp the image. It does give the edges. So how to sharp it? So if I want to make the edges of the image more prominent, I add these edges to the image. So this is what I can do. This is my image, right? Image pixel. Add the derivative of this with C. It means that how much I want to highlight. I will add that number to it, and I get this thing. If you see here, okay, so this is the image. Okay, this is the edge, and this is the sharp image. These two are the sharp image, but two different kernels. One with this, one with this. Okay, so if you are using this kernel here, you add. But if you are doing, because this is opposite to this, so the edges will go the other way around. So here I have to put C equals to -1. Okay, so these are the same thing but with different filters. Okay.
It is here, right?
Okay, I get your confusion. This is image. This is not image. This is just its edges. I separate the edges, not the image. Okay, I get these edges. Okay, let's say you have some picture, okay, of the tree. Okay, so this is one picture. The Laplacian will not give you the image, but it will just give you the edges. Okay, once I get these edges, but as your confusion, okay, what should I do with this? Because this is not the picture, right? So what I will do, I will add this and this. When I add this and this, what it will happen? The edges will be enhanced.